Okay, I think we can get started. Hello, good morning to everyone, and welcome to the 14th session of the Probabilistic Machine Learning Reading Group. Today we have Jose Manuel Camacho, who recently graduated and is now a doctor, and we want to start by congratulating him. And he is going to talk about decision making under uncertainty, a topic really very related to his PhD thesis. Welcome, Chema, and the floor is yours.
Uh, Thank you for the introduction, Paulo. Yeah, I will be presenting chapter 34 about decision making under uncertainty. I will be covering several problems of decision making under uncertainty. In particular, I will start with statistical decision theory. Second, I will cover influence diagram. Then I will move to A/B testing that will allow me to introduce contextual bandits and Markov decision processes. And then I will end up with active learning. So about the statistical decision theory, the motivation is that Bayesian inference allow us to update our belief about hidden quantity in light of some observed data, while decision theory is the framework that allow us to turn this outdated belief into action. So in statistical decision theory, we have a decision maker or an agent that in light of some data has to choose an action A. And this agent is in an environment whose state of nature is unknown and represented by H. And he has a loss function that represents the loss of taking action A when the true state of the environment is H. And a policy or decision procedure that given data X will say what decision to take. The goal of the decision maker then is to choose the policy that minimizes the risk or expected loss that is given by the expression in the screen. And this risk can be defined from either a frequentist or Bayesian perspective. So the slides summarize the key distinction between the frequentist and the Bayesian approach given in the chapter. We have that in the frequentist approach, the state of nature is treated as fixed but unknown, and a policy is evaluated by its risk over repeated dataset generated under the unknown state, while in the Bayesian approach, the observed data is fixed and the state of nature rate is treated as an unknown random variable. In this case, we use the posterior distribution to compute the posterior expected loss and choose the action that minimizes it. One advantage highlighted in the chapter is that the Bayesian approach is constructive. So once compared to the frequentist one. So once we observe the data and specify a loss function, it gives us a direct way to build the optimal policy. So as I said, more specifically, in the Bayesian decision theory, we have the observed data X that is fixed, while the state of nature is unknown. So we use a prior distribution over this state of nature, through which we compute the posterior distribution, and then the posterior is used to compute the posterior risk of a given action or policy. The optimal policy is the one that minimizes the posterior risk. So The chapter also illustrates some single decision-making problems that arise in machine learning and shows how they can be handled using the decision theoretic approach that I just presented. One example is classification. In this setting, both the state of nature and the action correspond to class labels. The state of nature will be the true label, while the action is the predicted label. In this problem, it is considered the 0-1 loss, where the loss is equal to 1 when the predicted label is different from the true label, and equal to 0 when the prediction is correct. So both labels are equal. Under this loss function, the posterior risk becomes the probability of making a wrong prediction, and therefore the optimal policy is simply to choose the label with the highest posterior probability. In other words, we assign the input to the most, we assign like the most probable class according to the posterior distribution. So then another example that is given is of single decision-making problem in machine learning is regression. Here, the state of nature is the true real value quantity that we want to predict, and the action is our prediction, which is also a real number. For regression, we typically use the square error loss that measure the square difference between the true value and the predicted value. With this loss function, the posterior risk is the posterior expected value of this square difference. And when we minimize this posterior risk, the optimal policy is the correspond to the posterior mean. One second. So the chapter also mentions other example of single decision-making problems that appear in machine learning that I will just mention. So one example is the parameter estimation of the model, where the goal is to estimate the unknown parameters of the machine learning models. Another example is structure prediction. In this case, the model has to predict an output with several dependent components rather than a single label of value. For instance, in natural language processing, the output could be a full sentence or a sequence of words in tasks such as machine translation. Finally, the chapter also discusses failure-aware decisions. These are especially important, like with the new regulations, where we do not want the model to focus only on accuracy. Instead, in the framework, we incorporate some fairness principle so that the predictions or action behave in an appropriate way across different groups. So that was all about statistical decision theory. So we will move to influence diagrams. So influence diagram are a graphical tool that allow us to represent structured multi-stage decision problem. They are an they are an extension of probabilistic graphical model that have three types of nodes: oval, that are called chance node and represent random variable; rectangle, that are called decisions and represent action; and the diamonds, that are called utility or value node and represent the utility of the agent. These diagrams you have three examples of these diagrams on the screen, and they are quite flexible. And this is a great advantage as they allow to represent a wide variety of decision problem. So given an influence diagram, we can compute the optimal policy by modifying the the variable elimination algorithm that is covered in section 95 of the book. I will go through the main intuition, that is that we consider the decision sequence of the scenario backwards, and then for each decision step, we compute the optimal decision, assuming that the following decisions are chosen in an optimal way. So the influence diagram that I just displayed were used to represent the decision problem for one agent, but influence diagram can also be extended to problems with multiple decision makers. When these diagrams represent a decision problem with two agents, it is called B-agents influence diagram. The diagram on the left represents a sequential decision problem in which the agent D will take her action that A will observe before making his decision. Both decisions will have an impact on will be the input of a random event whose outcome together with the decisions of each agent will determine their utilities. This diagram allow to analyze the decision problem. I mean, one advantage is that this diagram allows to analyze the decision problem of each agent in a separate way and are useful for modeling competitive and adversarial scenarios, such as those studied in adversarial risk analysis. That is one topic my PhD thesis was about. That's all about influence diagrams. So we move to A/B testing. So in A/B testing, we have two alternatives, and we want to decide which one performs better. Performs better in an A/B test. A is typically called control, and B is called treatment, but they can also be called arms. So in an A/B test, it is followed a test and roll approach in which there are two phases. In the test phase, it is randomly assigned user to each of the treatments. It is measured the accumulated reward for its action. And after observing the test result, we apply a decision rule to select the action that appears to be the best. And then in the second phase, it is called the rollout phase, it is deployed that action to the remaining of the population. There are two key considerations in A/B testing. The first is the decision rule, how to choose the better action based on the noisy test result. And the second is sample allocation, how many users to assign to the treatment and how many to the control during the test phase. In the sample allocation consideration, it is important to know the exploration and exploitation trade-offs, since assigning more users to the test phase give us more reliable estimate, but it also leaves fewer users for the rollout phase, where we are going to be deploying the action that we decide was the best. Therefore, let's say that texting too much can reduce the total expected reward that you will gain at the end of the process. So the chapter have introduced a Bayesian framework for A/B testing through a concrete example. What I have done to present it is I have extracted the main idea. So I will start by introducing the notation needed to, let's say, display the approach. In particular, the y vector denotes the vector of rewards collected from action j during the test phase. The parameter mu j represents the expected reward of action j. Nj is the prior mean reward of action j, and nj is the text sample size assigned to its treatment. So to compute the policy, what you do is choose the action with the largest posterior expected reward, while the test size for the treatment, for the control and the treatment are chosen to maximize the expected total reward. This total reward is the sum of two terms, the expected reward during the test phase and the expected reward during the rollout phase when using the optimal policy. The expected reward during the test phase is the sum of the sample size weighted by the prior mean reward of each action. In contrast, the expected reward during the rollout phase depends on the decision rule after observing the test result. It is computed with the last expression in the slide. We can compute the regret of a policy to measure how much expected reward loss compared with the policy of an oracle that knows the best action in advance was lost. So the regret of the policy is the difference of the expected reward given perfect information and the expected reward of the chosen policy. We have that with perfect information. The oracle always select the action with the larger true mean reward. We have that lower regret means that the policy is better since it performs closer to the perfect information oracle. So this A/B testing allow us to introduce contextual bandits. So A/B testing was a one-state decision problem in which we take treatment zero, we take our treatment and control a fixed number of times, observe the reward, and then we deploy the bet action to the remaining population. This can be generalized in what we will call the bandit setting, in which the problem becomes a sequential one. In fact, we will make an action, we will observe a reward, we will update the policies through which we'll perform another action. And so the policy will be adapting as new rewards are collected, and these adaptive policies can increase reward and reduce regrets. So I will go deeper in this bandit setting. In particular, for bandit problems, we can distinguish between two main settings. The simplest case is the multi-arm bandit. At each step, the agent chooses an action according to its current policy and then receives a reward from the environment. The goal is to quickly identify and exploit the action with the highest expected reward. And then the case that we are most interested about is contextual bandit that adds an extra layer of complexity, and where before choosing an action, the agent observes the state and the policy then select an action based on the states, and the reward depends both on the state and the chosen action. And at sorry, after each step, the agent obtains a new observation composed by the state, action, and the reward. All this information is used to update the policy and improve future decisions. So in contextual bandits, mm, the goal is to maximize the expected cumulative reward. We can at the same time distinguish between two settings. The finite horizon case, where the agent interacts with the environments for a fixed number of time steps, and the objective is simply the sum of the expected rewards collected over all those time steps. And in the infinite horizon case, the interaction continues for a limited number of time steps. And what it is done to keep the objective bounded is to introduce a discount factor gamma between 0 and 1. This discount factor will give less weight to reward part in the future. So depending on the choice of this parameter, the agent will emphasize on immediate rewards or long-term rewards. So here again, we have the exploration and exploitation trade-off. At each step, the agent must decide whether to explore by trying different actions in order to learn the reward function better, or to exploit by choosing the action that it appears to give the highest reward. The difficulty is that the agent might be exploiting too early. It might be relying on bias or incomplete data, and it can get stuck in a negative feedback loop. So what it is done, like to get the solution for contextual bandit, is to define a belief state as that is the posterior distribution over the reward model parameters. This belief state summarize what the agent has learned from the previous context, action, and reward. After each new observation, the belief state is updated deterministically using Bayes rule. Bayes rule. Then this updated belief can be used to compute the predicted distribution of the reward for each possible action. Usually computing the exact optimal policy from this belief state formulation is untractable, so you cannot compute this, so you will need to use approximations. In the chapter, it has been covered two important methods that are upper confidence bounds and Thomson sampling. So we start with the upper confidence bounds. Um, the main principle behind this method is the optimism in the face of uncertainty. That means that the agent will construct an optimistic estimate of the reward uh, with with high probability is designed to be an upper bound of the true reward function. The thing is that you will be choosing uh, greedily from these estimates. And as at the start, you will have higher uncertainty. There will be a larger exploration bonus that will encourage exploration, while as the agent collects more data, the uncertainty will decrease and this bonus will become smaller, and the policy gradually will shift toward exploitation. So the other method is Thomson sampling. And the idea is to choose its action with probability equal to the probability that is the optimal action. In practice, this is implemented using a sample then exploit strategy, in which first we sample a set of a set of reward model parameters from the current posterior distribution, and then treating this with this parameter, we greedily choose the action that maximizes the reward. And similar to before, at the start, the posterior is uncertain, so different samples of the parameter will lead to different actions, and this will encourage exploration. But as more data is collected, the posterior becomes more concentrated, and the sample models will become more similar, and the method will gradually move towards exploitation. So let's say that the idea is like kind of intuitive, but it is very effective in practice, as at least as the book says. Then from contextual bandits, let's say we add an extra layer of complexity, and we move to Markov decision processes. So we have that contextual bandit assume that action affect the current reward, but not the future states. Markov decision processes, or NDPs, what they do is to generalize this setting by allowing action to affect future states. NDP is defined by the tuple that you see in the screen, that is composed by the state space, the action space, the transition model, the reward model, and the initial state distribution. So the key difference between NDP and contextual bandits is that actions influence not only the immediate reward, but also the states. So yeah. So two important concepts in Markov decision processes are the value function and the Q function. For a fixed policy, the value function, that is also called state value function, measure the expected discounted return when the agent starts in a state S and then follows policy pi, while the Q function, or action value function, is similar but also fixed the first action. It measures the expected discounted return when the agent starts in state X and takes action A, and then follows the policy pi afterwards. Uh, yes, so we have that a policy pi is optimal if it achieves the highest value in the value function for every state. The optimal value functions are denoted by B star and Q star. A central result in Markov decision processes are given by the Bellman optimality equations. This equation expresses optimal decision making in a recursive way, where the value of the decision is the immediate reward plus the discounted expected optimal value of the future state. And once the optimal value function is known, we can uh, derive the optimal policy by acting greedily. In particular, if we know the optimal Q function, the optimal policies simply choose the action with the highest Q value in each state. So in an equivalent way, if we know the optimal state value function, we choose the action that maximize the immediate reward plus the discounted expected value of the next state. The problem of solving the optimal value function, Q function, and policy is called policy estimation. So the chapter also covered planning in Markov decision processes. And so if the Markov decision process is known, so that means that we have all the elements of the tuple. The process of computing the optimal policy is called planning. If the model is unknown, the problem is instead addressed using reinforcement learning. That is the topic that is explained in chapter 35. In this chapter, it has been explained um, three planning methods that can be grouped into dynamic programming and linear programming. Let's say that for large or continuous spaces, the planning versions of these algorithms are not good enough because the problem becomes intractable. So it is used an approximate version of these algorithms. Then we move with the last problem that is covered in the chapter, that is active learning. So the motivation for active learning is that in some settings we cannot label all the available data. Instead, an agent must decide which data points are more useful to label in order to train the model in an efficient way. And this is especially useful where labels might be expensive or time-consuming to obtain, such as in medical image classification or expert annotation tags. So active learning by selecting informative sample can often achieve higher performance with fewer label data than random sampling. And the goal of this framework, of this setting, is therefore to maximize learning while minimizing the labeling costs. In the book, uh, there are covered three active learning scenarios. The first is membership query synthesis, where it is assumed that the agents can generate an arbitrary data point through a query and ask to an oracle that knows everything to provide the label. In practice, this is not common. It's more of a theoretical interest because uh, you require a good generative model and access to an oracle on demand, and that's not going to happen. Um, the second scenario that is commented is the stream-based selective sampling. Here, the agent will receive input one at a time in a stream, and at each step, it must decide whether or not to request the label. Again, this scenario is mainly of theoretical interest. The scenario in which we focus is pool-based sampling. In this setting, a pool of a label sample is available from the start of the process. At each step, an acquisition function will score the candidate and select the most informative sample that are those that have a higher score. Then once the labels are obtained, the model is updated and the process is repeated. And we stop when the budget, the put, or target performance is reached. So let's say I will show an example of pool-based sampling active learning. I also like to motivate let's say, this section of the talk. So the model is a logistic regression classifier applied to a small data set. And what we see is that in panel A, the model is trained only on few data points, and it has an accuracy of about 82%. Then in panel B, what we see is that the model have been trained with 11 extra data points that were randomly sampled. And we see that the accuracy increases slightly, around 85%. But then what the panel C displays is the points that are selected through active learning, where the accuracy is with the same number of data points, the accuracy is greatly increased to almost 97%. So this illustrates the main advantage of active learning, that by selecting more informative points, we can achieve better performance with, let's say, the same budget that you have for labeling. So the chapter also emphasized that active learning is closely related to other sequential decision problems as Bayesian optimization and contextual bandits. It says that all three can be can be seen as sequential decision problem, but that they differ in the objective and in what they query, while active learning queries label, Bayesian optimization will query function evaluation and contextual bandits, action and will observe then rewards. The idea is that all three methods try to make informative decision while using as few queries or action as possible. So, as I said before, in the pool-based sampling, we use an acquisition function or strategy that will allow us to decide which labeled point should be query next. We will focus on three common active learning heuristics that are uncertainty sampling, query by committee, information theoretic methods. And the purpose of all these strategies is the same: to identify the most informative sample to label so that the model can learn in an efficient way with a limited budget. So we start with uncertainty sampling. And the idea is that it selects the point for which the current model is most uncertain about. I will be covering these strategies through classification, a classification problem, but this can also be applied to regression. So we have that for each point, our model, our classifier will output a vector of predicted class probabilities, and that it will be P of n. And then we will also define P1 and P2 as the largest and the second largest predicted class probabilities, respectively. We have that different uncertainty sampling strategies use different acquisition scores. So we have entropy sampling that selects the point with the highest predictive entropy. We have margin sampling that select the point with the smallest difference between the two class probabilities. And we have the less confidence samplings that select the point whose class has the lowest probability. At the end of the day, all these methods, what they do is trying to identify the points where the model is more unsure about to obtain the label that might be more useful. So I have extracted this sample from the book that illustrate how different uncertainty sampling strategies can select different data points. Here, the model has to decide which sample to query, 4, 5, or 3. For each sample, the upper plot shows the model predicted class probabilities, while the lower plot shows the uncertainty score assigned by each heuristic. We have that using entropy sampling, the selected point is the middle sample. Using margins sampling, the selected point is the right sample, and using the less confident strategy, the selected point is the left sample. So what this shows is that different acquisition function can lead to different query choices. So you have to be careful. But in practice, margin sample, the chapter said that is the one that work better. Uh, Another strategy is query by committee. Um, the idea here is to use disagreement between several models as a measure of uncertainty. This is especially useful for models such as support vector machine that usually do not output class predictions. That usually output class prediction and not probabilities. So what we do is we train a committee of K models, and for each point, like we count how many models, both for each class, and we from it produce an empirical distribution that we will use with the same strategies as before: entropy sampling, margin sampling, uh, less confidence. Um, so another statement that the chapter does is that this strategy often outperform like the, let's say, vanilla uncertainty sample. It can be seen in this example where the model with the query by committee sampling reached the top performance using way less points. It is also compared with some random samples, and also like the purple solid line is the mean of the random sample. Um, the another approach that the chapter speak about is Bayesian active learning by disagreement, or BAL, which is information theoretic method. The idea here will be to query the point whose label is expected to provide the most information about the model parameters. In other words, we can say that we want the label that will reduce our uncertainty about the model the most. In this case, the acquisition function can be written as the expected Kier divergence between the posterior over parameter after observing the, the new label and the current posterior before observing it. And at the same time, this can be rewritten using the entropies of the predicted distribution. So there might be sometimes where it is not efficient to just query a data point at the time, and that's why the chapter introduced batch active learning, where the idea is to select a batch of a labeled sample at once rather than just using one at the time. And this is useful because imagine that it in some cases you have to query one data point and retrain the whole model, and this again and again, this can become very slow and computationally expensive. The chapter introduced batch val, that is the batch version of the method I saw before. And in this case, instead of scoring each point independently, it selects a batch whose labels usually provide the most information about the model parameters. The key idea is that with this method, it is taking into consideration redundancy between points in the same batch. Um, However, to compute like this method, we will need approximation as the acquisition function is generally intractable. So to conclude, I have included an example of convolutional neural network on MIS using both BAL, and BAL. Um, what we see is that in the first panel, in panel A, uh, BAL select individually informative but often redundant sample. As you can see, we have like the same number in the batch in all the cases, while batch val will select more diverse sample within each batch. As you can also see, for instance, in the second batch, all the numbers are different, the same for the third one. And what we have with this is that the batch version result in more efficient learning, so we can reach higher performance, as we can see in the last panel. So that was all. I don't know if there is any question.
Uh, I think I'll start. I have a few questions. First of all, thank you for the very interesting talk. Regarding the active learning possible criteria you've shown, in the uncertainty related ones, I I was thinking that all these three uh, possible metrics could select, like for example, in the image example, they could all select an image which is pure noise, because in general, classificator would give you similar probabilities for all classes, and because of that, the entropy would be as high as possible, the margins as low as possible, so on. So then, what's the meaning of this criteria in such example?
I mean, you are right. In fact, that's one thing that the book comments. And in fact, that's as far as I understood, that's like one motivation for the information theoretic methods that are most robust to that situation that you're describing.
Ah, okay. Okay, yeah, that makes sense. And then also the query by committee, I don't think I understood it well. You have several, like you have different models, or just, yeah, right?
Yeah, you have,
But
yeah, you will be considering just several models.
yeah, so in the example, you are comparing several models against one model trained with just one of the metrics, or what? Because if not, the like at the end of the day, if you're just using the query by committee thing to get an estimate of the original metric, you should be having a noisier selection, and because of
Yeah,
that,
yeah, yeah.
you should be having
You
worse
are.
results, and they are much better here. So, any intuition on why is that?
I mean, yeah, I mean, you're right. I think they only use one model. I mean, yeah, you are using the committee to select the model, but then the one that you are, I mean, the one that you are computing the accuracy for is just one of those.
Yeah. So
That's
then,
the
why
main thing.
why is it so much better if at the end it's just a noisy estimate of the same metric you were using before and had an exact expression for?
I mean, that's a very good question. Uh, to be honest, I don't have an intuition about that. I mean, it's just one thing that the chapter goes through, and I think that the statement that he does is maybe because there are some empirical results about that. But yeah, I don't have an intuition about it.
Okay. And my last question would be related to the last, I think the very last slide, the last example, where you were
Oh,
comparing bold and batch bold. Yeah, so here you are using bold to still select the batch, right? And that's why they are redundant.
Yeah, that's it.
And
In,
do you know how they could compare if you were doing an iterative update? So just using bold to select one against using batch bold to select a batch. Do you know which one or any like proof logic into which one would be better?
uh, oh, that's also a very good question. I mean, I think that's I don't really know. I mean, my intuition, yeah. I mean, in like in practice, that could not be made. I mean, because it would be too expensive. But I mean, I think my intuition will say the simple batch. No, sorry, I will go for the batch valve because as the chapter comments in how the acquisition function is contracted, I feel it could get more informative samples. But it's just intuition. I don't have more result about that.
Okay, thanks. Are there any other questions?
I have another one. Very early in the talk, you introduced these ideas. Like you didn't cover them too much, but maybe you do have an intuition on fairness-aware decision making. And you said something about like there's new laws relating the usage of fairness-aware decision or fairness-aware losses instead of other kind of losses. I don't know if you have I know how these decisions are implemented or based on what, like what are the risks of not using fairness-aware decision or losses in general.
I mean, so the thing is, I mean, the risk will be like it might be that the model in very high stakes scenarios will, let's say, be biased and determine and make, let's say, an unethical decision. And they do this by, like, um, if I remember well, they define the loss function and they make sure that it respects some proportion between different groups or populations. Did that respond to your question?
Yeah, more or less. Yeah. Thank you.
Following, can I have another question?
First.
Yeah. Following that same discussion, what do you think about the exploration exploitation dilemma in adversarial environments? Like exploring, sometimes agents explore actions just to maximize the reward, and there are some states that are dangerous, and just taking into account the highest reward may not be the best. So, is there any strategy or any laws that takes that into account? Maybe regret or something?
I mean, that's a very interesting question, but to be honest, I don't have intuition about that. So, I mean, I am not a practitioner in those topics, but yeah, I mean, like taking like an adversary into play is something that it it's really interesting and needs to be considered.
Thank you.
Thank you. I don't know if there are any other question. If not, I think we can conclude the session. Thank you so much, Emma, again for your presentation. And yeah, the next session will be on causality. It will be given by Fatima Sanchez Cabo, and it will be on June 3rd. We have had to postpone it 1 week. So
Okay.
I hope to see you there. Thank you so much.
Perfect. Bye bye.
Thank you.
Thank you,
Bye.
Chema.
Bye bye.